This is Dr. Holt. This is one of the WebAssign problems that is fairly challenging. Part A, this part is not too bad. I'll show you how to solve that problem. First thing again is draw your free body diagram. We would have, and I'm going to start first, is just break the components of the mass. We've done this many times, but I'll just do it over again. We know right now that this value here is going to be your theta. This would be mg. And this value would be mg cosine theta. And obviously this should be mg sine theta. At that point, go ahead and draw the regular free body diagram. Tilt your axes. This force here. This, oops, I got the wrong one. Force coming back up here, which is your normal force. You'll have a force coming down here. Now you're going to have friction coming down here also, and you're going to have this force coming back up this way. Now the force of the spring, you're going to label it as kx. This will be F normal, and then this would be the mg cosine theta, what we just did a second ago. This would be mg sine of theta. Okay, so now the questions basically says what's the extension of spring the instant it begins to move. So the instant it begins to move, we're talking about static coefficient of friction. So this value here would be your F normal. F normal would be the same thing as mg cosine theta. So we'd have mg cosine of theta times mu of s. So now all you have to do is sum up your forces in the x direction and set it equal to 0 because just about to move. We would have, I'm going to let this one be positive, be kx minus mg sine of theta minus mg cosine of theta times mu of s. Alright, is equal to 0. Alright, so we can say immediately we'll solve for kx here. I'm going to erase this a little bit down here. I know we started this problem earlier. Get this out of here. Okay, kx would equal to mg sine of theta plus mg cosine of theta over mu of s, static friction, or times mu of s. Okay. Now what we're going to do, we're going to solve for the x value, so we're going to divide everything here by k. Okay, and that's going to give us the answer to part A. Because A says, basically it says what is the spring deflection? What's the extension of the spring itself? So this is the value that you have. Okay, what I would recommend on this one is go ahead and just pull out mg over k, and then you're going to end up with sine of theta plus mu of s times the cosine of theta. And that's going to be x, and what they did, they labeled that as the d value. Okay, that's part A. Alright, now part B is a little different here. It's going to be an energy type problem. It says the block stops moving just as extension of this contracting spring reaches 0. Express mu of k, the kinetic coefficient of friction, in terms of mu of s and theta. So what we're going to do here, and again let me get rid of this because we're going to work this earlier, is draw yourself just a rough picture. So bring this up. This is going to be your angle. We will draw a small block here, like this. We'll take that in position. We're going to clone this, bring it up to here. Okay. Now what's going to happen is this block here is going to have a 0 velocity when it's at the bottom and the spring's getting ready to pull it up, and then it's going to stop up here. Now what is happening as it slides along here, you have kinetic friction operating on it or acting upon it. So we're going to make that to be Fk. That's going to be your kinetic friction. This distance from here up to here represents the distance. And this is going to be this value right here. That's the distance that spring has stretched. So we're going to set this up and do it with the conservation of mechanical energy with work being done by the non-conservative force. So if this distance here is d, then if this is theta, then this has to be d times the sine of theta. Alright, let me scroll down a little bit here. So we're going to write this up as the potential energy gravitation 1 plus the potential energy of the spring 1 plus the kinetic energy 1 minus the work done by the non-conservative force must equal to the potential energy gravitation 2 plus the potential energy spring 2 plus the kinetic energy 2. So this will be position 2, this will be position 1. Alright, so we're starting here. We're going to let this basically be our neutral axis. We're going to take everything off of this one. So we know our gravitational potential here has gone to 0. Alright, we know our kinetic energy here has gone to 0. Okay, we stretched this spring as far as we can, so this does have a value here, and we also have the value here. Now as we get to the top, we've come to a stop completely, so the kinetic energy here is also 0, and the spring over here is no longer operating once this object has stopped. So this is 0. So we're going to set this up as 1/2, and we'll do it this way first. We'll set this up as kd squared minus our frictional force, which in this case is going to be mg times the cosine of the kinetic friction here, and then we would multiply that by d because it's going to be operating along this d. That would be minus, and we will set that equal to our mg times d times the sine of theta. Okay, now we're going to simplify. We'll divide everything by d. This will cancel, and this will cancel here. So now we're down to 1/2 k value, and now we're going to put the d in, and the d again is all this times mg over k times the sine of theta plus mu of s times the cosine of theta. Again, that's all like that, minus mg cosine of theta, sorry I forgot theta right there, times mu of k is equal to mg sine of theta. Okay, so now what we want to do, go ahead and scroll down a little bit. We'll go ahead and multiply this. Now this is all being multiplied by 1/2. We will simplify what we can. Now we can divide everything by mass. Mass has gone here, here, and here. Oops, let me get rid of that. Okay, gravity, we can get rid of it here, here, and here. We can also lose our k value here and here. So now we're down to 1/2 the sine of theta plus 1/2 mu of s cosine theta minus, sorry, almost put mg, minus the, forget for the theta, sorry about that, minus cosine of theta mu of k is equal to the sine of theta. Okay, we're trying to solve for mu of k. So I'm going to move this over and move the sine over. That's going to give me 1/2 the sine of theta here Okay, and then plus 1/2 mu of s cosine of theta minus the sine of theta is equal to cosine of theta mu of k. Okay, simplify again. We can add these two together here. So now I'm down to 1/2 mu of s, the cosine of theta, minus 1/2 the sine of theta is equal to the cosine of theta mu of k. At this point, we're going to divide everything by the cosine of theta. And when I do that, look what happens here. I get 1/2 mu of s minus 1/2 the tangent of theta is equal to mu of k. We'll pull the 1/2 out, and we will get mu of s minus tangent of theta is equal to mu of k. Okay, fairly complex problem, the second part. The first part was pretty straightforward. But this is how you're going to get the answer to the homework problem where you're asked to find mu of k. Alright, best of luck.